Welcome, ladies and gentlemen, to the SAME Energy and Sustainability webinar titled Enhance Sustainability Through Microgrid Applications. I'm Samal Harbison with SAME National Team, and I'm here to help in the background for today's webinar. But before we get started, let me go over a couple housekeeping rules. You have entered into the webinar in a listen-only mode, but we ask that you double-check your phones to see if your mic is muted. All questions we ask that you submit in the questions tab, and we will answer those at the end of this presentation. You may download the PDF certificate and the PDF version of today's presentation in the handout section. Today's webinar is recorded and will be viewed for later. Now I'd like to turn it over to the ENS COI Chair, Michelle Sipe.
Hi, everybody. Thanks so much for joining us this morning. Just wanted to give a quick COI update to keep everybody in sync with what's happening. Jamel, if you want to hit the first one. So JETSI is quickly approaching. We want to get a little reminder for you if you're interested in presenting at JETSI for 2021. It will be in Portland, hopefully. We're going to have the themes coming out late November, early December, so please be on the lookout for that. If you have a topic that you would really like to share, please consider submitting. Also, we are looking for volunteers that are interested in reviewing the abstracts and to help develop our ENS track. If you haven't done it, I highly recommend it. You have a really good opportunity to see some really great ideas and drive that track for us at JETSI. If you're interested in doing that, please reach out to our volunteer engagement lead, Marcellus. And then lastly, if there's a webinar topic that you're really interested in, we are looking for insight from our membership. Please let us know. You can contact either myself or Norm and give us an idea of the topics that you would like to see in 2021. Also, if you would be interested in presenting yourself, please let us know and we'll see what we can do to add you to our webinar list for 2021. So with that, I will turn it over to Norm.
Thanks, Michelle. Before we get started, we got a couple of polls we'd like to run through. So if you would be so kind to let us know what sector that you represent. I think Tamal's going to give you a few seconds to click into that one. All right. Oh, good mix today. Nice, very good. And our next poll question is your job function. You'd be so kind as to share that with us. All right, technical, good. Engineers, you're going to like this one. This is a pretty good technical presentation. And our last poll question, are you actively looking to implement a microgrid? All right, super. Okay, good. So I'd like to take the next couple of moments to introduce our speaker for today. Alex Creviston is our chief engineer at Go Electric, which is a Saft company. Helped found the company in 2011 and has been very active in the automotive world for many, many, many decades. And this is a culmination of the application of automotive principles to microgrid systems. And he's in Indiana and resides close to the plant in Muncie, and has a BS in physics from Ball State. And with that, I'm going to hand over the microphone to Alex so we can kind of walk through this presentation with you. And please remember, if you have any questions, just type them in the question block, and then we'll be able to respond to those at the end. Thanks. Alex?
All right, we'll go through this presentation. This lists out some of our control philosophies and some of the things that we brought to bear in designing our power electronics and control systems for microgrids. Some of this is based on the previous history of myself and one of the other co-founders, primarily coming out of automotive systems. So we'll start with grid definitions. These are Go Electric definitions. They're slightly different than the Department of Energy definitions, and they align with some of our control strategies. In a macrogrid, individual loads and sources are not statistically significant. Control is based on slow-moving averages and trends. Macrogrids are made up of large numbers of things, so each item only has a small impact. Macrogrids are based on centralized generation, and they're top-down control. They're extremely stable and predictable, but they're not agile. A microgrid is a system where individual loads and sources are statistically significant to the control and management of the system. The control is based on near real-time fast measurements and updates. You typically have a small number of things, so a larger impact per device. All microgrids must contain generation, typically referred to as distributed generation. That site generation may be thermal standalone, solar, wind, or storage coupled with power electronics. Microgrids are fast and agile, but require different controls. All non-storage electrical generation grids are zero-sum systems. So all energy produced is immediately consumed. The system sums to zero at all points in time. The power conditioning and operational parameters are controlled at the generation source. It's top-down control and it's push only. So in other words, with these equations, the supply equals load at all times. The controlled grid has massive inertia, and that damps uncontrolled loads and absorbs shocks and smooths the system. Micro changes in rotational energy manifest themselves as micro changes in frequency and voltage. And those small frequency and voltage changes are instantaneous balancers, but they average out over time. This is where we get into some of the parallel systems with mobility. Vehicle systems are also zero-sum within steady frames of operation if you have no acceleration or deceleration. A mechanical transmission decouples the prime mover and frequency from the wheels, so it gives you a mechanical differential solution. It optimizes the prime mover, somewhat damps the system, provides smooth operation. If you have an energy mismatch, if the supply and the load don't equal each other, you have a change in kinetic energy of the system. The kinetic energy is either stored as vehicle velocity or spent as waste heat in a traditional vehicle platform. So with the transmission, the energy in equals the energy out, but the torque is decoupled from the prime mover to the wheels and the frequency is decoupled. Gains or losses in the system energy manifest as changes to kinetic energy to the system. Now, there are some similarities between hybrid electric vehicles and microgrids. Braking and acceleration are uncontrolled kinetic energy change events. The system cannot anticipate those changes, so a fast control response system is required. Inverters decouple electronically, providing an electrical differential solution between the sources and the loads. So the instantaneous syncing or sourcing of energy from the kinetic energy change events enhances the control of the system and increases the efficiency. The energy flows do not have to be symmetric. So the electrical energy storage is used to balance the system, and it's not all manifested as changes to kinetic energy anymore. This translation of kinetic energy changes between storage and motion is the fundamental concept of hybrid electric vehicles. The time shifting from negative kinetic energy events to positive kinetic energy events is the energy storage solution for hybrid electrics. The energy storage balances the kinetic energy and allows mismatches in frequency, voltage, and current of the drive system through the power electronics. It decouples with an electrical differential solution. This graph illustrates a kinetic energy shift. So the energy is stored and shifted from the negative kinetic energy event to the positive kinetic energy event instead of being wasted as heat. So on the left side, we start out in a steady state condition, and then you have an uncontrolled negative event. Basically, you hit the brakes. So you are releasing energy. On the right side, you then reaccelerate back to a steady state, so you're gaining energy. The shaded boxes down below show the transference of energy from one form to another, from kinetic to chemical and back through the power electronics. So the shaded boxes are now the energy shift that was previously wasted. This uncontrolled kinetic energy changes in a mobile system is analogous to uncontrolled distributed generation. So renewable systems such as wind and solar are not controlled sources. Changes in output may be extreme and cannot be anticipated. So now our zero-sum equation has actually changed. So the load does not necessarily equal the controlled source anymore because you have a new term. The regulation system has two terms to balance against, and one is now high speed with the uncontrolled energy. Uncontrolled systems typically have little inertia, so the regulation systems must be fast to maintain stability. So with little or no internal damping and high rates of possible change, large, slower systems may become highly stressed or unstable. The mainline thermal generation is unidirectional. The energy never flows backwards. So the controlled energy can only go to zero. It cannot sink energy. So if the uncontrolled energy is a large percentage of the controlled energy, you'll have large and fast swings of uncontrolled. It can and will happen. If the uncontrolled energy becomes greater than the load, the system is mathematically unstable. If the grid rotational energy cannot account for the uncontrolled energy sources, major instability issues will arise. To counter this, we can install a power electronics storage system as an additional term in the equation. So we change it again. So the storage yields a new bidirectional controllable variable to balance the equation. So the uncontrolled energy is countered by the high-speed storage system so that it can resum to zero at all points in time and make the controlled energy behave much better. The microgrid sinks or sources energy as needed to stabilize the main power feed. So the high-speed, low-inertia microgrid can smooth peaks and valleys, complement relatively low-speed grid control. The high-speed inverter behaves like a damping inertia on the uncontrolled energy feed and effectively becomes synthetic inertia electronically. The bidirectional energy storage is identical to the time-shifting leverage of kinetic energy in hybrid electric vehicles. It's a transference of energy from one form to another. This next graph shows all of the different energy terms graphically. So you have load, you have a controlled source, and uncontrolled, and the balancing of the storage system. The bidirectional flow in the storage microgrid results in a level supply from the controlled energy. It helps base load it, and it slows the required system response back down to controllable time frames. So the time shifting energy covers multiple uncontrolled transients. The controlled energy system stability is greatly increased with synthetic inertia. The shaded boxes here show transference of energy, same as the hybrid electric system with the high-speed storage, countering large fluctuations in the uncontrolled energy. The next couple of slides discuss briefly the differences when we talk about 4-quadrant control between motor control and grid power. In motor control, 4-quadrant systems, all electric vehicles and hybrid electric vehicles are this type. The voltage, current, and frequency are variables and can be constantly changing. You have 2 torque vectors and 2 velocity vectors. And the velocity changes, as in frequency changes, are required for proper operation. These quadrants are nearly mirror images, as motoring torque and generating torque are substantially the same. High-speed quadrant shifts are required for normal operation. Between quadrants 1 and 2, you switch between motoring and generating, acceleration and braking, sourcing and sinking, effectively time-shifting energy. The torque vector reverses and the phase angle shifts from leading to lagging. This is what drives the torque vectors to positive and negative, and then results in transference of energy. 4-quadrant grid power is a little bit different. You always have fixed frequency. The voltage and currents are variable. The frequency is static for proper operation. The voltage is a variable, but it's in a very narrow range. You have 2 real vectors, which are kilowatts, positive and negative, and then 2 not as real vectors, which are imaginary power, but very real current. Circuit limitations typically limit combinations of the real and reactive power, summing to a maximum. So if you have 100% real power, you have 0 room to move on the reactive power, and vice versa. Full quadrant shifts are typically along the kilowatt axis. So from, say, 1 to 3, from source to sink, and the phase angle shifts from positive to negative. Pure power in kilowatts can be produced or absorbed, and pure kVAR can be added or subtracted, or any combination thereof. So operation anywhere inside the ellipse on the right allows the inverter to enhance the system by providing different levels of both power and reactive current. We link these inverters like any other AC connection. They're parallel connected to a mainline grid. We leverage the power electronic speed to pick up line fluctuations, so we balance and stabilize the system. This allows for peak shaving or kVAR correction. It allows for economic dispatch or energy time shifting. And it allows for instantaneous power feed and autonomous islanding without the need for spinning reserves, which yields energy security with a high-speed islanding operation. You can stay on when the grid goes off, which is exactly the same as shutting off an engine in a hybrid vehicle. And you can transition between different modes at will. This chart shows a transition between states where you have the grid present and you're running along in parallel operation, and then you have a grid loss. So with 4-quadrant power operation, your positive and negative real power, and then leading and lagging VAR. The grid is analogous to an infinite inertia motor. You cannot change the fundamental frequency of the microgrid. So if kinetic energy is related to inertia times the frequency, if the inertia is infinite, then changing the frequency requires infinite energy. And attempts to change that frequency will manifest as current sinking or sourcing. The harder you push or pull on the grid, the more current it takes. The inverter controls the phase angle relationship with the grid, and that controls the primary output current. Voltage and frequency are followers. So the microgrid is leading and in charge. We are a grid-tied system at this point. So if we're going to transition to an islanded operation with a grid loss, you have the grid present with infinite inertia, you have a grid loss, and you can sense an inertia shift So the frequency change is now possible where it was not before. You change control states and move into an islanded system. In an islanded system, the mode shifts from support to lead. So the inverter now controls the frequency and voltage. This operation is identical to fixed frequency motor control. So at a fixed speed, frequency and voltage stay the same and current is varied to meet required torque and motor control. It's another parallel between the two different systems. When the grid returns, we sense it, we sync to it, and then we go back into a support mode. We change the control states and we turn to phase angle support mode. So the graph on the right, the grid's present, we're following with phase angle control. We sense a grid loss, we go into islanded operation. When we're in islanded operation, we're forming the system with voltage and frequency control, so we become the prime. When the grid returns, we do another control state transition back into phase angle control with current support and kVAR support for the larger grid.
All right, thanks, Alex. And to help put some of that theory into real-world applications, I think what we wanted to do was run through a couple of use cases to help explain how those functions apply in the real world. Because the key component to this is to try and make sure that there's a balance, an energy balance that allows you to have the microgrid perform at the speed that you need with the scope that makes sense. So this first case study or use case is in Twelly Army Depot. And as you can see on the picture on the upper right, they have a 2 megawatt solar array, but it's a concentrator system, so a little bit different. And in this case, what the customer was looking to have was kVAR support. And we're not really the microgrid here per se. We are part of a SCADA system, and we operate to inject kVAR to help balance the entire transmission distribution system based on the operation of the solar systems. And to be able to do that, as Alex mentioned, was to be able to have that 4-quadrant control so that we can operate on the kVAR side and control the kVAR side of things as well. On the technical specs, it's a 1 megawatt with a 1 megawatt hour battery, and that is the middle image is the footprint of the microgrid system. And if you can take a real close, we'll take a real close look. The actual microgrid system is are the 3 boxes, 3 brown boxes in the middle, and you can see that the footprint based on the theory in application is very small. It does not require a large amount of space. One of the other things that's a benefit of this kind of an idea is that you can have for all intents and purposes, a microgrid in a box and ready to go and be deployed quickly. That same picture on the right-hand side, the larger brown box is your battery. And then you've got your transformers that go along with that. So it's been operating for several years now, very successfully as a component to the SCADA system that serves Twelly's distribution needs. And we're in some discussions for phase 2 to attempt to do some other things on the site based on the phase 1 operational parameters.
This system is typically running in the hundreds of kVARs to help the power factor and reduce quite a bit of the current loading on the utility input line, which was also getting a little bit stressed by the site.
So it definitely serves multiple purposes. And I think this next use case is really one of the most interesting ones that we've encountered, but also one that shows why you need to have the kind of balancing that was discussed in the theoretical part of it. And this one here, again, from a sustainability and a resilience standpoint, comes out very, very strong in that 29 Palms has a tank firing range 500, which is a remote location, not connected to anything. They have a solar system in place, 150 kW worth of solar, and then 2 diesel backup generators. And the system was intended to run fully off of solar and have the generators operate only when required, maybe low light days or something along those lines, or for night operations. And what was happening was that the solar system was unable to stay online and continue to trip off. And the generators were now the primary source, and the California Department of Environmental Management was not very pleased with this, because those were supposed to be backup generators. We were tasked to solve the problem and create a grid here, a mini grid for all intents and purposes. And what we did, what we found was very intriguing. Alex can walk through some of the technical aspects of the limitations, but they have a 15 kV system that controls the targets, and that's a buried system. So it's not above ground, which now all of a sudden you end up with a very high impedance situation. On top of that, the operating power factor was negative 0.05, which it's hard to come by something like that. That had everybody scratching their head. To kind of not bury the lead, but what we did was we installed the microgrid system so that it would properly utilize a battery and our controls to maximize solar output, and have the range operational at all times with minimal use of the backup generators. This system has been operating autonomously now for almost a year after our solution was commissioned. The generators have run a couple of times, and basically in support to build up the battery, not to manage the operation. So the generators are now there to bring the battery up to a proper state of charge, because the solar system wasn't able to manage that. So your runtime is reduced dramatically on those generators. Matter of fact, one of the generators, we've already requested that it be repurposed because it's extraneous. It can be moved someplace else on base and used for some other purposes. But again, the theories that Alex went through for how to balance that energy load, this is now in a complete remote location, and you can expand this higher or from the 150 kW and make it grow. If you can grow the solar system, you can see how this balance can be in effect, and you can have a remote grid or an islanded grid even inside of a campus or a military installation that operates in the same principles. High use of renewable energies with minimal use of generation assets.
So to summarize, the systems to store and dispatch fast and unpredictable flows of energy are fully analogous between hybrid electric vehicles and inverter-based microgrids with storage components by energy transference. So store and dispatch systems can substantially improve efficiency in a drivetrain, and combinations of distributed generation and high-speed power electronics can enhance the security and efficiency of a bulk power system in a similar way. Control algorithms used for rapid quadrant shift and motor control can be tailored for use in power inverters and grid connections. A 4-quadrant grid power inverter coupled with storage can greatly increase the flexibility and scope of a microgrid and can have a beneficial impact to overall stability, particularly where renewable penetration is high, or as in the case of 29 Palms, renewable penetration is 100%. The utilization of motor control philosophy indicates a parallel connection and treatment of the grid as an infinite inertia motor. And these always-on connections allow for fast peak shaving and load leveling, as well as auto islanding options for security.
All right, so thanks, Alex. This would be a good time if you have any questions to go ahead and post them. We do have one question from John Klein, and it was, did you use a 4-quadrant inverter? And I'm assuming this is for the use cases that we discussed.
Every system that we put out is a 4-quadrant inverter, so that the power factor at 29 palms, it was 0.05. It was also capacitive. So it wasn't even a normal inductive power factor. And that's one of the reasons why we do that, is so that we can handle those types of situations, in particular ones that tend to have thermal generation on them, because the generators basically won't run in a leading power factor. So we always put in 4-quadrant systems to allow us both maximum flexibility, and then make sure that when we get to the sites, we can cover any required or any unexpected things that we find.
Great. So there's another question, is how fast can the system respond?
There's a couple of different answers to that. If you go back into the switch gear, then the switch gear mechanical operation is one limitation, and that can be upwards of, say, 20 to 60 milliseconds. In terms of the actual electronic sensing, there's something that takes place, but that's usually in 4 milliseconds or less. And then when you get all the way down into the power electronics, current updates typically take place at the fundamental switch frequencies, which are between 4 and 6 kilohertz. So you're down in the or you're down in the microsecond range, basically, for current updates, and then it kind of cascades up. The control systems are typically based on a layered approach, so that the things that are required to be handled quickly are handled quickly without communications, and then overall site things are done through a little bit different structure and can be handled slower. But basically the system update time is around the 4 to 8 millisecond time range.
All right. Let's see. Are there any capacity limitations to this system, and what can be done to increase resiliency when dealing with large systems of 10 megawatts or higher? Is there a layered approach for larger application?
In theory, there's not a limitation to this style of control. It comes back into some of the site dynamics and whether or not, or how many systems are paralleled, and then what kind of differential loading that they see. So it's somewhat of a complex answer. In theory, putting in 1 megawatt blocks and putting them together would yield the same level of control as doing it in a smaller system, but then you start getting up into dynamics between the lower voltage battery systems and the medium voltage distribution systems, and how those work together becomes a little bit of an unknown. So that would be one of the caveats in looking at much larger systems for this style of control.
Okay, good. So there's a question of what contract was used to fund this work. The Twelly contract was a, it was, I want to say it was a SIBR contract for that one. The 29 Palms was direct funded from the operational budget at the base. This does fit into, so putting a little bit of a different hat on, the way these systems operate and how this design works can fit well into a ESPC, UESC, and or a PPA if it's attached to solar. I hope that helps. It can go in either third-party finance or regular funded projects. We're going after all those. Another question, what drives your equipment selection decisions? I'm assuming that has to do with the equipment that's operating the microgrid, not necessarily the integration of it. If that's not correct, Rich, please help me understand that one.
In terms of the inverters, there's some that we've been working with for some period of time, and we have a very high comfort level with our capacity to integrate with their internal control systems. And there's a couple of different manufacturers that we have very good relations with. The power magnetics are all internally designed. And then in terms of the switchgear, we tend to stay with one switchgear supplier simply because we know them and we know how to lay out the systems. If you go back though to the fundamental thing of the inverter, it really went back to what inverters could we get the level of control that we needed to have to run these style systems, and that drove as much of the selection as anything else.
Okay. Let's see. Well, that didn't work out too well. Did any of the solutions include load control on the use cases? In these two cases, they did not. However, there are several other use cases where that is part of the landscape. So it can operate under load control. It does operate for load control. And since systems are integratable with either SCADA or BMS, it's flexible as to how and what kind of loads you would like to manage.
If you go back to one of the earlier microgrids, which was the Spiders microgrid layout, it utilized both seamless islanding as well as load control on the larger system. So part of the load went away in the case of a grid loss and part of the load stayed on, and then the overall microgrid was rebuilt throughout the larger campus over a period of minutes. So that one was kind of a mixed case use where you could withstand the shock to the system until you could bring up additional thermal generation. Sometimes we use load control so that it maximizes or it minimizes our economic impact on the site. And sometimes we just let go of non-critical items when we go into islanded operation.
Okay. Let's see. ROI. What is the ROI from a financial perspective on examples provided? The Twelly was ROI independent because they needed to have K-bar control for operations. Wasn't part of the dynamics of that project. However, there is a component of utility billing changes if you're billed on a KVA versus a KW. We've not done that kind of an analysis on that one because it's more performance based. The 29 Palms was the ROI on that one was less than a year, but that was based on the penalties and fines that the Department of Environmental Management was going to slap onto the Marine Corps. So in those, as we find, we do different projects. The financial metrics vary depending on what the problem is trying to be solved. So go ahead, Alex.
Well, in the case of 29 Palms too, and some of the other sites that we've seen, there's some hidden benefits that a lot of people don't think about, and they don't manifest themselves until you put these systems in. And a lot of that has to do with the backup generators. And this was true at 29 Palms. So the generator is running lightly loaded part of the time, which is a death sentence for a diesel engine. So when we put our systems on, one of the things that we do when we ignite thermal generation on site, we actually load it to close to its maximum, which ensures that the system doesn't wet stack, and then you're also getting maximum efficiency out of the engine. So the maintenance on the engine goes down and the usability of the engine goes up. And that's somewhat difficult to actually put an ROI on, but it is a real benefit that a lot of sites actually see.
Okay. Are any of the systems imported from overseas? No. This is all BAA compliant, and everything is manufactured and sourced in the United States. As far as the reliability statistics and performance metrics, we have those established, but they're based on individual projects and whether they're meeting the project's goals, and if we are hitting the marks that the customer wanted. on a general basis for the equipment or the solution, I'm not really sure if that would work as like a mean time between failure type application or not. Mostly because if you've seen one microgrid, you've seen one microgrid. They're very unique currently. Thanks. And Rich reminded me it's Tuella, not Tuelle. Sorry, us Midwesterners pronounce things a little bit differently. Let's see. That brings us to the end of the questions. There was a comment here about a follow-on load control. Certainly happy to run through that because there's the systems themselves are very flexible, and this could be any microgrid system, not just the ones we discussed here, in that you can participate in either what I would call demand control for your own native load, and we have some ideas that we can now potentially participate in demand response and still meet cybersecurity requirements. So there's some good financial applications, but there's also there's distinct technical reasons and theories on load control. We'd be happy to discuss that. Yes, that's the last question here. For maintenance agreements and warranty, there was warranty for the installation, a typical 1 year, but there are O&M contracts that are associated with that. Especially on a microgrid system, the battery is not a place and forget type application. It needs to have some maintenance done on it. And the microgrid system, it has upgrades, software updates, and things along those lines where we find improvements that need to be handled, or if there's some things that occur. So we do have those in place at both locations, not both locations. At 29 Palms, there's a local electrical contractor that does the majority of the O&M for the base for that system. And they call when there's a really serious issue, of which we haven't encountered any. What is the future of microgrids for facilities that are looking for greater resiliency when grid tie-in is currently primary power? Jason, that's a really good question, and we see the future as being, I'm going to call it the right-sized microgrid, as opposed to controlling the entire base or the entire complex, where you go in and you harden yourself for the critical loads that you have identified. Data centers or control centers. A project that we're working on right now is down at Fort Hood on a tower, on a control tower for the flight line. Places where you cannot host any interruptions whatsoever. And I think part of what Alex was discussing was that the capabilities, if you build the system correctly, you get a seamless transition. And I think there's a piece in there that may have not been connected so well, but the way this design is you're live connected to the bus at all times. So you're actively synchronizing in real time at all times, which now allows for seamless transition because you're using the battery to balance it. And I think Alex can explain that a lot better than I can.
Yeah, if you're running along in parallel operation and you sense a grid loss, basically what happens is the inverter ramps up its output current, and then we send a signal to open up the grid tie breaker so that the site doesn't lose power. And so that's the grid loss scenario. That happens in real time, and it happens seamlessly and in about a quarter of a cycle, maybe a half a cycle, depending on what the fault actually is. So the site doesn't even know that it's lost power because the power electronics carry it through, and then you can bring on additional thermal generation, or it runs off battery for some period of time, or it gives you a controlled shutdown. It kind of depends on what the site is actually wanting. In terms of larger sites, this kind of goes back to the spiders thing again, where instead of trying to run an entire large campus on a seamless transition or a bumpless transition, then you can have a portion of it stay seamless and a portion of it rebuild after the fact using a combination of power electronics and thermal generation. In a building by building scenario where you have grid power, if a system like this is put on, the easiest way to think about it is that this forms a parallel UPS system. So instead of a double conversion UPS system, this system actually is not putting out full power. It's not running the site until it has to, so that it can sense a grid loss and keep the site operational, but it doesn't really have a constant power loss associated with it like a standard UPS does.
Yeah, and NREL has referred to that as grid catching, based on analysis of our implementation and systems. So it literally catches the grid under any three-phase fault. But again, that's based on the theories of the mobility theories in application versus more of an industrial theory and application. So, all right, I don't see any new questions in here. Anything? Cool. Yeah. Okay. It looks like we've got a good discussion, so hopefully that worked. Kamel, I'm going to hand the keys back over to you.
Thank you. Thank you, Alex, for a great presentation, and Norm moderating the question portion. Appreciate you guys taking the time out today to give such an informative presentation. If you guys have any further questions that you want to ask that you think of later, here's the contact information for Norm, and he will pass that information along to Alex. An upcoming event that we have is the 2020 Virtual Small Business Conference. It's being held November 4th through the 6th. Please you can find information here at smesbc.org. You can go there, look at the registration prices, and to see the things that we're offering this year for SBC. I'm trying to tell you, you don't want to miss out on this great virtual event. You will find great value at the price it's being posted. So thank you again, Michelle and Norm, Alex, for today's presentation. And for the attendees, please view the handout section for the PDH certificate as well as the PDF version of today's presentation. Thank you, guys.
Thank you, everybody.